talking about solubility rules, whether or not something is soluble or not. So right away, I need you to grab the sheet that I gave you, and I want you to have this at your disposal through the entire video. In fact, we're going back to this all the time. The number one thing I want you to look at when we look at this are 4 variables at the top here, A, B, C, and D. It's really important as we follow all these rules that we follow them in order. In other words, if there's a rule in C that we go, oh yeah, that's a rule that we can apply. If there's a rule in A that we also can apply, we apply the rule in A before we apply the rule in C. Yeah? So let's talk about some terms here. So soluble means dissolvable. Insoluble means indissoluble. A better way of saying this is that soluble things will not form a precipitate or a solid, but insoluble things will. What does that mean? So if I have any 2 ions and I bring them together, anytime you bring 2 ions together, they're going to do a solubility check. They're going to decide whether or not they want to connect, form a precipitate, or ignore each other. So if 2 things come together and they are soluble, they will pass on each other. If 2 things come together and the rules tell us that they are insoluble, they will form a solid or a precipitate. We want insoluble. So let's start with the rules. So the A stands for acids, and in particular strong acids. What we're really looking for though is anytime that we have an H together with anything, we're going to follow the strong acid rules. So if you have an H and you put any of these 6 things with it, it will be soluble. The way I remember it is CBS PIN, hydrochloric, hydrobromic, sulfuric, perchloric, nitric. I forgot hydroiodic, it's missing in here. That's what the I stands for. So if you're trying to add onto your diagram, there should be this as well. But anytime you have an H plus and you try and put it with anything, it's going to do a solubility check. And if you, for example, wanted to put it with a Cl minus, it's going to say nah, and you're going to get no reaction or no precipitate. Another way of looking at it is this. If we were to ever have HCl outside of water and we were to throw it into water, it would immediately dissolve or break apart. However, what if we had anything other than these 6? Now I include that HI in there as part of these 6. If I had anything other than those 6, like for example, let's say I decided I wanted to put acetate together with this. We look at the list, is acetate part of these 6? Nah. That means that these 2, when they hit into each other and they do the solubility check, they'll realize that they are insoluble. And remember, we love insoluble because that will form a precipitate. Now, a precipitate, I'm going to use the word because in the past we were using the word solid, but sometimes things will form as liquids. Liquids and solids both are precipitates. So what's the opposite of an acid? Well, a base. Now, in these kind of generic terms, acids have H pluses that we have to worry about, and that's how we know we follow the A rule. Bases have OH minuses with each other. Now, again, we're going to put things with OH, and we're going to try and determine if they are soluble or not. Now, these are the only things that are soluble with OH. In other words, these are the only things that if we put them with OH, they will do nothing. Now, what's a little bit tricky is this idea of group 1. Now, if you take a look on the periodic table, group 1, those right there, from lithium all the way down to francium, those are group 1. So if I put, for example, potassium plus OH minus, we'll look down at the rules right here and say that's part of group 1, therefore it'll not form anything. However, if I take anything that's outside of this, like literally any element or any metal that's outside of this, it will form. For example, if I took Al 3 plus, and I put it together with OH minus. Well, let's look at the rules here. Is Al3 plus part of group 1? Nah. Is it strontium, calcium, or barium? Also, nah. Therefore, this will form, and remember, whenever we're writing a new compound, we have to balance off the charges. So this is going to be AlOH in parentheses 3. Now, I know that's being covered up there because I didn't slide it over enough. But one of the things you need to be aware of here is that this OH3 that I have here that I've covered up, there's 3 of them. So in order to balance this, I have to put a 3 right here. What I've just done is I've just written a net ionic equation, which we're going to talk about in the next video. Before I forget, this one strong Calbert thing, you may be like, how does that help you as an acronym? The previous example was CBS PIN. it was just a nonsensical thing. One strong Cal Bear. Back in the olden days, I lived up in the Bay Area, and the University of California, Berkeley, their mascot was a bear, as you see right here. And their football team was ranked #1 in the nation, as hard as that is to possibly imagine. So one strong Cal Bear they were #1, and they were strong Cal Bears. And it's kind of neat because strong is SR, Cal, CA, and Bear is BA. If you have to memorize it, that's how I'd memorize it, one strong Cal Bear. Okay, so we're always going to follow the rules. So we're going to start with A, is there an H plus? B, is there an OH minus? And then we're going to go through the compound rules, the C portion. Now there's two parts to this. The #1 part is NAG-SAG, and you're going to be like, what in the world? So it's an acronym that I use to help me remember all of the elements here that we're trying to determine if they're soluble or not. Or by elements, I mean polyatomic ions or groups. And I think of it this way: if someone's like, nag, 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 and you're like, oh, and you sag, nag-sag. So what this means here is this. Nitrates, for the N, are always soluble. That means no matter what you put with NO3, no matter what, it will always say, I don't want to be with you. So if you have nitrate, this is nitrate right here, and any other positive ion comes in contact with it and was like, hey, would you like to connect? NO3 will always be like, no, and we'll go its separate way. 100% soluble. So one of the cool things is, if you ever see nitrate in our reactants, we know automatically that that nitrate is not going to do anything. Similarly, ammonium, NH4+, and if I were to write it out here, I go like this. If I have an NO3, it does not matter what I put in front of it, every single time it's going to be soluble. If I go the opposite way and I have NH4+, this is ammonium, it doesn't matter what I have after ammonium, it won't form. So I can have anything on the end of this, sulfate, it doesn't matter. Ammonium plus anything equals soluble. And then lastly, group 1. Now, we mentioned group 1 before. Remember the periodic table, the lithium down through rubidium side. Group 1, if you put them with anything, now these are, I say group 1 cations sometimes. If you put them with anything, it doesn't matter what the tail end is, they're going to say, no, I don't want to hook up with you. So these three things, if you ever see them, either in your reaction to begin with, or if they're giving it to you and asking you to determine if something is soluble or not, they will never hook up, so they will always be soluble. And if you were to take them already made and throw them into water, they would break apart 100%. Let's go to the SAG portion of this. SAG is also an acronym, and the S stands for sulfate. So anytime you have a sulfate, we're going to assume that they are soluble. There are only 4 exceptions: Cal, Bears, Stir, peanut butter. Calcium, barium, strontium, and lead. So if I happen to have calcium and SO4 2-, and I'm trying to put them together, they will form a precipitate. Why? Because these 4 are the only things that are not soluble. So we love that because this is what they will form. Now this weird Cal Bear Stir peanut butter thing, if you've ever been near Cal Berkeley, it's a very crunchy place. You can't like throw a rock without hitting like a drum circle or like a hacky sack group or whatnot. So I imagine that they eat their peanut butter, not in the way that we've grown up, we're in the Jif jars or whatever, but I discovered this abomination, and my wife actually buys it now, where you have oil on the bottom, and then you have like the peanut buttery mixture on the top, and you have to stir it to be able to eat it, and the great thing is it has no sugar in it. But I use the acronym Cal Bears Stir Peanut Butter because it works out really nicely. Cal, calcium, Bear, barium, Stir, strontium, and PB, it doesn't work quite as with lead, but peanut butter. Just a reminder, everything with sulfate is soluble unless you have Cal Bear Stir peanut butter, in which case they would be insoluble, and that's really what we're looking for. Now one of the first ions we learned was acetate, C2H3O2-, remember? Acetates, no matter what you put in front of them, they are soluble. So if I have an acetate ending and I try and put anything with it, it's going to say nah. But you have to be careful, because I don't know if you remember back at the very first example we gave was, what if we put H plus C2H3O2-? Now, here's the thing. We follow the rules in order. So if we get to the nag-sag rule and we couldn't apply the H rule or the OH rule, this acetate will hook up with nothing. However, as soon as we get a rule we can apply, and you see I have a hydrogen right here? This hydrogen tells us that we have to follow the CBS pin rule. And the CBS pin rule says only those 6 acids are soluble. Everything else is insoluble. And since acetate's not part of CBS pin, it would be considered insoluble, and we would end up with HC2H3O2. But if we tried to put anything else with this, let's say we tried to put Pb2+, literally I can go through any other thing with acetate, and it will always be soluble. So group 7, and I would encourage you whenever you're doing any net ionic equations or solubility rules, you have your periodic table in front of you, and always take a glance and look at group 1, because those are ones that are going to be involved often, and then take a look at group 7. Now group 7, those are the halogens. They start with fluorine and go all the way down to astatine, which we never really use. If you ever have a group 7, in other words, a chloride, a bromide, a fluoride, so any of these, so like Cl or Br or anything, and you try to put anything with them, they will be soluble. Unless you put these 3 ions with it, and those are the only times that they will be insoluble. And the acronym I've come up with, actually a student came up with a few years back, was polar bears hug aggressively. It's delightful. Polar bears, PB, hug, HG, aggressively, AG. So if I put with this Pb2+, I would look at the rule right here and I go, well, normally group 7 would be soluble. But Pb is our polar bear, which is insoluble, which means these 2 things will hook up. Anytime you hook up 2 things, you must balance the charges. So this would be PbCl2. Again, in order to write a balanced equation, we would have to put a 2 in front of this. And remember, when they're by themselves, they are minuses. So anything in group 7 will always be soluble unless it's with polar bears hugging aggressively. Now here's the thing. If you've gone through the A, B, and C, so is there a hydrogen, is there an OH minus, nag-sag, do any of those ions impact us? You're going to realize that there are a number of ions that aren't included in that list. Think of all the ones that we learned: phosphate, chromate, thiosulfate, perchlorate, permanganate. All of those are not accounted for in the rules. So the compounds part 2 is the sweeper rule. Now, what is a sweeper? It means if you cannot apply any of the previous rules, you then apply one of these 3 rules. Remember, do not jump to these until you've checked out and made sure that none of the other rules that we've done can apply. For example, if you were to see a compound like this and you were to see CaCO3, and I'm going to play the game soluble or insoluble right now. So if I go through all the rules, is there an H+? Is there an OH-? Is there a nitrate, et cetera, all the way through nag-sag, none of these rules apply to this. None. So then what I do is I look at the negative ion. The negative ion, we always know what the charge is because we've memorized them. We happen to know that CO3- is a 2-. Therefore, this would be insoluble because all -2 charges and -3 charges are insoluble if none of the other rules apply. So calcium carbonate, if we were to take it and throw it into water, it would not dissolve. But more importantly to us, because we care about this more, if we were to take Ca2+ and try and put it together with CO3 2-, we would look at the rules and we'd say it's insoluble, which is what we look for, which means that these 2 things would connect and would form CaCO3. Let me do one more example here. Let's say I gave you something like this. MgClO4 in parentheses 2, magnesium perchlorate. Now, I'm not going to go through all the rules, but if you go through all the rules, none of them apply. Now you may think, well, there's a Cl here. Isn't there a rule for Cls? Yes, for Cl. This is perchlorate. It's not Cl. So therefore we go to the charge rule and we look at perchlorate and we realize that it's a -1. Therefore, it is soluble. So, as we close this up, make sure when you're doing all of your net ionic equations in the next section that you have this table with you and you apply the rules in order, A, B, C, and D. Hopefully it's been helpful. I will see you in the next one.